find the right end rate, the process we use in generating end rate guidelines, and the challenge farmers face to find the balance among yield, profitability, and nitrogen loss reduction. Our first speaker, Guolong Liang, is the Commercial Vegetable Agriculture Water Quality Outreach Specialist and covers the Central Sands region of Wisconsin. Today, Guolong will be presenting on end rates and yields in common cropping systems in the Central Sands and why it's tricky for farmers to balance the two. You can go ahead and share your screen, Guolong.
Awesome. Thank you, Sherry. Let me know if you can see my screen.
I can see it.
Thank you, Sherry. Well, hello, everyone. Thank you for taking the time this afternoon to hear more on nitrogen management. In today's webinar, we would love to start tackling this ambitious challenge, right? When we're trying to balance yield, profitability, and water quality, when we're trying to plan for our nitrogen program in this upcoming 2026 season. My presentation is packed with a lot of graphs and data, so buckle up as we try to tackle this challenge one graph at a time. First graph. This is the Venn diagram basically showing the challenge that we're poised here, right? How do we, at the center of these three circles is end decisions. How do we make nitrogen decisions can really have different levels of impact on all three factors that our farms care about. Today, we'll focus on nitrogen rate specifically within nitrogen decision making and think about how much nitrogen should farmers really apply to get these three outcomes at the same time. What I want to focus on today in terms of water quality is nitrogen leaching. Let's start with some fundamentals to get a refresher on nitrogen leaching. Let's start with how does nitrogen leaching actually happen within our individual farm fields? Well, nitrogen leaching requires two factors to occur at the same time. Nitrate, as one of the forms of nitrogen, is available for plant uptake, but also is prone for nitrogen to be lost. The first factor is when too much nitrogen is present in the soil, right? It can be either from the nitrogen that we supply through fertilizer, manure, biological fixation from previous crops, or from mineralization in the soil organic matter. And the second factor is a drainage event. It can occur through precipitation, such as snowmelt, as well as rainfall. And because of differences in precipitation, soil texture, as well as the evapotranspiration of the crops that we're growing, the patterns of these nitrate leaching events can really vary year to year, as well as crop to crop. One thing to remember about nitrogen loss patterns is that it can not only happen during the growing season, but also in between two growing seasons. Growing season here is defined as planting of the main cash crop to the harvest time, and the shoulder season were defined as the harvest time till the planting of the next crop. In the case of corn, we usually think about the shoulder season as the time period between November and April to May. In the early 2000s, researchers tried to understand how nitrogen leaching happens, about the timing as well as the amount of nitrogen loss through leaching in the continuous corn system. They evaluated leaching using using equilibrium tension lysimeters, and found that 73 to 75% of total leaching losses happened in between the 3 months between April and June. This makes sense, right? When we have in these 3 months, we usually have heavy rainfall or snow melt, which causes drainage events. And if there's no cover on the ground with an elevated amount of soil residual nitrogen, then it causes higher risk for leaching during these 3 months. However, this pattern can look quite differently if we move to a different crop rotation in the cropping system. Here today, we're looking at potatoes, where in this rotation, the leaching pattern looks quite differently. In this rotation, the grower planted sweet corn, followed by potato, field corn, and peas. Over the 4 years, researchers found that over close to 360 pounds of nitrogen were lost through leaching throughout the 4 years. In this study, we saw that 40% of the total leaching amount happened during the growing season, and 60% of the total leaching happened during the shoulder season. The data collected here was from 2016 to 2019 on a field with plainfield loamy sand. Within this trial, they observed different leaching patterns across different crops that was in different parts of the rotation. Again, I'm stressing here that there can be high temporal variability when it comes to leaching patterns on our ag soils. And when it comes to how this can be applicable to farmers, right? How understanding leaching through direct measurements, such as using lysimeters, can be difficult to apply on individual farms. But we can still collect enough information to make good decisions on nitrogen. And one of the approaches that we're going to talk about today, both me and Dr. Ruark, is nitrogen rate trial. Nitrogen rate trial is an excellent tool for us to understand how does yield, profitability, as well as nitrogen loss, especially nitrogen leaching risks, can be influenced by the amount of nitrogen that we apply. Before we dive into a data set, just to warm us up in terms of looking at different graphs, let's look at a typical yield response curve to nitrogen fertilizer. In a typical nitrogen response trial, we are set up with usually strips with 5 to 6 treatment nitrogen rates and monitor yield within each of those treatments. What we see in most crops is that as nitrogen rate increases, crop yield will increase, but only to a certain point. Then it will essentially plateau when we won't get a higher yield with more nitrogen being applied. We can then use an approach called economic optimum nitrogen rate approach to understand at what point where we reach this economic optimum rate where if we go past this nitrogen rate, we are not getting extra profit from the extra amount of nitrogen that we apply. Dr. Ruark actually did a great presentation later last year on this specific topic on how to build and read a nitrogen response curve. So my colleague is going to drop a link in the chat so that you can watch that presentation at a later time. Meanwhile, nitrogen that is not removed by the crops continues to accumulate as we see this yield plateau, right? So how can we use a similar approach like this to inform growers on their own nitrogen management practices? Well, we can use this graph to evaluate how to adjust where on our current nitrogen management rates. And broadly, we can divide this graph into 3 different zones. If we're in the yellow, agronomically, we're probably not reaching the optimum rate, optimum yield yet. At the same time, we also have relatively less environmental impact, especially to the groundwater, when it comes to leaching compared to the other 2 zones. If we're in the red zone, then it's basically a lose-lose situation, right? We're not necessarily making more profitable, we're not making more money past the economic optimum end rate, while the nitrogen leaching risks continues to increase exponentially. Well, if you're in this blue zone, then first of all, good job. We're probably getting closer to this optimum end rate. And the next steps would be to think about fine-tuning our nitrogen rate based on all of our other outcomes, such as water quality, where you might experience marginal economic loss, right? $1 to $2 if we're talking about corn, while we can make major improvements when it comes to water quality in reducing the risks. Here's an example from a research trial in Iowa that kind of demonstrated the power of fine-tuning our nitrogen rate. In this study, researchers in Iowa monitored nitrate nitrogen concentration from a subsurface drainage study where they monitored the tile water essentially. Their N rates fall into the 3 zones that we talked about, with 4 rates under the university recommendation, 2 rates over the recommendation range, and 3 rates within the recommendation range. From this study, we saw that the exponential increase of nitrate leaching curve confirmed with our concept. Um, while at the same time, when they tried to reduce the nitrogen rate from 168 kilograms per hectare to 134 kilograms per hectare, they saw that a 20% reduction in the nitrate nitrogen concentration in the discharge water, which is getting us closer to the 10 parts per million for nitrate nitrogen, which is the drinking water standard. At the same time, I need to acknowledge that in reality, these curves might look way messier and more complicated, right? Especially in a cropping system like a specialty crop like potatoes. So in reality, the curves might look more like this. Some years you would have yield plateau at 400 hundredweight. Some years you might yield 600 hundredweight. So the challenge here is to find what is the realistic goal for my farm for this field uh, to plan our nitrogen around it, right? So that we can maximize the profitability as well as minimizing the impact to groundwater. So how does this theory play out in real life data? So let's dive into an example where a potato grower basically used this approach to fine tune their nitrogen program. It was back in 2024 when this grower in central Wisconsin reached out to me and my colleagues at Extension to do an experiment within the nitrogen optimization pilot program run by DATCAP as well as UW to answer this simple question, right? Can I reduce the amount of nitrogen I apply at hilling where the potato growers build and rebuild their potato hills to reduce leaching and optimize for yield and profitability? To answer this question, we first looked at how much nitrogen they are applying as of their business as usual practices. For this russet variety called Gold Rush, they usually spoon-fed nitrogen throughout the season. In this specific year, they applied 23 units through starter, pounds per acre, and 21 units through broadcasting. And in total, 212 units of nitrogen when they rebuild the potato hills during hilling at two different occasions and supply the rest of the nitrogen through fertigation. In total, they applied 286 pounds of nitrogen throughout the season. So in this specific trial, the grower was interested to look at the 212 units and see if we can make potential reductions to this specific time period, which is reflected in this experimental design where we have the business as usual at the bottom of this table. And these rates where we manipulated a reduction of 15%, 30%, and essentially eliminating all nitrogen application at the hilling where we don't apply any during this period. Due to the time limit of today's conversation, we're not going to cover another side quest that the grower was also interested in, which was did the biological product helped with the uptake of nitrogen. We'll cover that in a different time, and we'll focus on the nitrogen rate responses as of today. In this trial, we evaluated yield, size profile of potatoes under each of these treatments, estimated farm gate income, as well as the surplus nitrogen within the system. Let's start with nitrogen, and let's start with the yield responses to the nitrogen. On the x-axis, we have the fertilizer N, ranging from 74 units all the way to 286 units. And on the y-axis, we have each of these bars representing the height of the yield under these N rates. Notice that this is 1 year worth of data. There's also like this big gap between 100 units to 200 units. And since we are only manipulating the hilling rates, we don't have a true zero N, which limits our ability to build a regression analysis where we can draw the curves. But what we can do is to do a pairwise comparison where we basically understand the differences between each individual treatment. So from this 1 year worth of study, we saw two major takeaways, right? One, we did not see significant increase in yield of potatoes across these three higher nitrogen rates. And two, we did see that the yield under business as usual was higher than that under the zero N and hilling treatment. At the same time, yield is not the only metric that the farmer cared about. He also cared about the marketable yield, which is the total yield minus the amount that we have green potatoes, misshapen ones, as well as the rest of the culls. So what about marketable yield when it comes to different nitrogen rates? Here we're seeing that marketable yield did not show significant differences across all four nitrogen rates. One thing we did observe was the differences in how these size profiles really differ across the different treatments. The three higher nitrogen rates had more large potatoes. These potatoes are larger than 10 ounces. And while the one received no nitrogen during hilling had fewer larger potatoes. This can significantly impact profitability because farmers' income are directly related to the marketable yield as well as the size profile that we just showed. So I talked to the farmer and they gave us two scenarios in 2 years, in 2 recent years in terms of prices. In scenario one, they had large potato tubers selling at $20 per hundredweight, and all the rest of the size classes selling at $8 per hundredweight. And in scenario two, which was from a historical different year, they only received $13 per hundredweight for the large potatoes, and the rest of the size classes stay the same in terms of price. Using these two scenarios, we can then build these simulations, right? How in each scenario, how much money can the farmer make under these different N rates? Let's start with the scenario number one. So in scenario number one, we can see that the trend of these responses basically follow the raw yield trend, where we have the highest income in the business as usual and the lowest income in the zero N and hilling treatment. But we do need to notice that statistically, the three higher nitrogen rates economic outcome did not differ significantly. And it also means that we can potentially, if we're prioritizing the farm gate income, then reducing the nitrogen rate by 30% might not be a bad idea. What if the margin was slimmer than the scenario one, right? In scenario two, we saw that that difference was essentially eliminated in a year where you get paid less for the larger potatoes. Although in this year, the larger N rates did bring more larger potatoes, it did not really yield a higher profitable income. So overall, we've looked at yield, marketable yield, as well as farm gate income. How about water quality, right? Here, we're not presenting on the direct measurement using lysimeters and other measures, but we can look at the balance between how much nitrogen that we're applying through nitrogen input and how much nitrogen the potatoes were containing when we harvest them from the fields as like a proxy to the leaching risks that we're onto. So in this graph, the yellow bars on the left are the nitrogen that we supplied through fertilizer, and the green bars on the right are the nitrogen that that was removed by the potatoes. You can also see the yield plot on the top of this graphic for comparison. We can see that as we apply more nitrogen, right? This unused N or excess N subtracting nitrogen removal by nitrogen fertilizer continues to increase, right? And especially when the yield starts to plateau, you can see that the jump from the third highest nitrogen rate to the second highest nitrogen rate increased when you applied even more to business as usual. And for the lowest nitrogen rate, we saw that the potatoes actually removed more nitrogen than the amount that we applied. This imbalance does not mean that no nitrogen leaching actually happened during the season. This can result from us not counting the nitrogen from other sources, such as from cover crops as well as from the soil. And since this is a trial in irrigated sand within central Wisconsin, what not to forget is about the nitrogen that's supplied through irrigation water. So we collected water samples from these pivots and collect and calculated how much nitrogen was supplied through irrigation during this specific season. For this well, in this specific site year, we saw that 55 pounds of extra N was actually added through irrigation. This partially pushes the lowest nitrogen balance closer to a zero, which makes more sense. And within the state, I would love for this conversation around nitrogen balance as well as the nitrogen content within the irrigation water to be more prevalent among farmers and agronomists. In 2025, our program, Ag Water, offered a outreach program named Nitrogen Insight, where we offer free irrigation water sampling for folks with pivots, and we can help farmers with reports on building nitrogen balances like these to help you understand nitrogen leaching risks better on your individual fields. So in the past year, farmers have gave us tremendous feedback on how they would like to, they've learned so much from the participation and they would love to continue in the future years. If you'd like to learn more about the Nitrogen Insight program, my colleague is going to drop a link in the chat where you can go to that program and contact our program staff as well as myself directly through that website. Okay, back to the trial. So what did we learn from this first year of potato trial? What are some overall takeaways, right? So we did see that within the three higher N rates where we reduced nitrogen from business as usual by 15% and 30% at hilling, yield and marketable yield did not differ significantly, right? And what's even more important is that in the lower margin yield, especially in this scenario where we're not getting paid at a higher rate for the larger potato tubers, we saw significantly higher leaching risks with not really significant increase in profit, especially under the three higher nitrogen rates. So these hopefully can help inform farmers' decision when they think about dialing back on their overall nitrogen application. So we brought this result back to the farmer and asked them how did they feel and then how will this impact their decision-making process. And this is a direct quote from the farmer. He said, I would be leaning towards reducing nitrogen rates for this specific variety in the future. And when we presented this result to other farmers, they said that they would want to design similar trials to understand the same dynamic on their own fields. Going forward, we would love to continue with the second year data collection as well as analysis, and then explore effects of other factors such as cover crops, the biologicals, and even explore the nitrogen use efficiency under these lower nitrogen rates systems in vegetables on the farms, right? So overall, what did we learn in the past 20 minutes? Here are some of the things that we covered, which include nitrogen leaching is just really hard to capture through measurement. But one thing that I want you guys to take away from this talk is that the timing and amount really depend on multiple different factors within the year. It can be the total amount of rain that we got in different parts of the growing season, as well as the shoulder season. And it can also depend on how much nitrogen, how much leftover nitrogen there is during different parts of the year. From the on-farm trial, we saw that excess nitrogen application can really increase our nitrogen leaching risks, right? Applying more nitrogen when we pass a certain threshold does not give us more profitability, but does increase our leaching risks quite dramatically. To end our presentation, I would love to call to some recommendation where if we want to find the balance among these three goals, right? Yield, profitability, as well as water quality, we need to have a good grasp of how my farm doing on an annual basis in terms of these three metrics. And in order to do that, one of the easiest and the most effective way is to do a nitrogen rate trial on your farm, starting with one field, right? To get the range of optimized rates for your priorities. Then after we understand the optimized rates, we can then set the realistic goal our priority is to reduce nitrate leaching potential on individual fields, as well as expanding that to the whole farm management. So hopefully by the end of this presentation, we have established a strong foundation on how nitrogen leaching can impact all these three factors and bring these solutions back to our farms and the clients that you work with. I think that's the end of my talk. I'll pass the mic back to Sherry.
Thank you so much, Guolong. That was a great introduction to the topic at hand, how it can relate to our Wisconsin growers, and a really good bridge to Matt's presentation. So as we are transitioning to Matt, we will be launching a quick demographics poll to collect some information from you. This is anonymous information. It helps us evaluate the audiences that we're reaching with this type of work. So please fill it out, as it does help us a lot. And also just a heads up, there will be a question as you leave the webinar that asks you about today's webinar topic. And that self-rating also helps us improve future programs. So for next year's webinar, if you could answer those questions, that is also a large help for us. Now, let me introduce you to our next speaker. Dr. Matt Ruark is a professor and extension scientist at the University of Wisconsin-Madison, Department of Soil and Environmental Sciences, and Discovery Farms co-faculty advisor. Today, Matt will be presenting on the process used to generate N-rate guidelines. So go ahead and take it away, Matt.
Awesome. Thank you, Sherry. And get those questions in the chat for those that are interested. Sherry, if you see any questions come in while I'm talking, feel free to interrupt me. There's a lot of
Okay.
details and a lot of different components, so it's always fun to, if we can get a little conversation going. I know the webinar format isn't always best for it, but so what I want to present on today is, so we're going to take you through, so Guolong gave us some interesting results. We're going to take you through another journey here. We're gonna talk about corn. We're gonna talk about nitrogen. We're gonna talk about utilizing these response curves and the power of these response curves in understanding what's going on in your cropping system and with your nitrogen management. So, big thanks to Monica Schauer. So, this work that I'm going to talk about is funded through DACAP's NOPP program, the Nitrogen Optimization Pilot Program. Want to thank, some farmer groups, Farmers for Tomorrow, as well as folks in UW Extension, as well as Portage County Land and Water. So, the presentations that or the data I'm going to talk about today, they are three sites. They are on sandier soils. So we're kind of sticking with a little bit of a sandier theme, but you can think about, like, as you every nitrogen response trial is its own special thing, right? And so we can look at these different trials that are getting different results and kind of work through them to think about, well, does it make sense what happened? One, and then what are the lessons learned, right? So we'll go through all this. So what we have is we've got three on-farm trials, and I've broken them into non-responsive, sort of responsive, and responsive, and the things we can learn from each of these. And so let's start with the non-responsive. So this site was on a loamy sand. Previous crop was soybean and 3 previous years of no-till. Um, there was a little bit of nitrogen out as starter, and then they started with nitrate rates. They didn't have a true zero. They started with 60 as the lowest rate and went up to 260. They also did a trial to evaluate molasses, and everyone, we can talk about that. But the nitrogen rates, these went out at 32% at a V6 application. First thing is, there's no difference with this molasses application, so we don't have to worry about molasses really. But hey, we want to test some of these things out. A lot of claims, no effect of molasses. But this also site, was it responsive to nitrogen, right? So we're going to talk, I know. So we have to also talk about statistics, and that's always everyone's favorite topic as we bore everyone with statistics. But if we use the first approach, it's like, okay, that's this analysis of variance, right? If we want to say, was the yield at one nitrogen rate different than yield at another nitrogen rate? We look at what we call the p-value for the effect. This p-value is larger than what we would say is statistically significant. Thus, if we were going to use ANOVA, like if we take this to, like, certainly we take it to like a publication, we'd say this wasn't responsive. There was no difference in yield among our treatments. Okay. But what if we pretended it was significant, right? And so this is the whole thing of like, well, do we use that ANOVA analysis of variance approach where we compare the treatments, or are we more interested in utilizing this and drawing a line through it? Okay, so here we go. We're going to draw a line through it and say, hey, we have this quadratic curve that we can fit. Isn't it wonderful? But of course, maybe some of you noticed this R squared up here, very low, 0.055. Now, keep in mind, right, when we want to say something is like highly predictive, you want this number close to one, right? This number is very close to zero. So that's the opposite end of the spectrum. Not very predictive, which is also what happens with these non-responsive sites, right? There's not a lot of change in the data. Um, in any case, so the regression wasn't that helpful, but technically we can still use it. We're gonna keep exploring here. Um, if we would use this curve, and we're gonna use a couple different nitrogen price ratios. So historically, we talk about this price ratio of nitrogen to corn. Typically, it hovers around zero point 0.1. Lately, it's actually here we're using 0.125 so it's saying like the value of, nitrogen's a little bit more expensive historically relative to the price of corn. In some cases, I think a lot of farmers are getting it based on what you're paying for nitrogen, what you might get for that corn price. It might be closer to 0.15. Yesterday we had a discussion with some with the farmer group, and some of them it might be closer to 0.18. In any case, so nitrogen's getting more expensive, so we're trying to credit that. In any case, so we look at this curve, it is flat, it's not fantastic, but 190 is where you'd technically maximize yield, but we use sort of this economic aspect and say, okay, but really you stop making money at 128. Okay. Um, Again, what if we don't care about statistics, right? So we're going to play around with this a little bit. Here's our yields, here's our nitrogen. So here's our nitrogen rates, here's our yields, here's the yield change. You can see like really you're getting most of the bang for the buck up to 100 pounds, and then really you're not getting much value past it. Um, most of that yield change is that uh, and so we're maximizing. If you want to talk about profitability on average, you did make an extra, in theory, you made an extra, what, 50, 65, I can't do math, 60, 50 to 60 bucks with that extra 40 pounds. You go from 60 to 100, you play the extra 40 pounds, you made some money, and then you definitely lost money after that. So as this farmer's looking at their setup here, not very responsive. Technically, on paper, if this average yield increase was true, they would have made a little money. But in reality, they're really maximizing the benefit with 100 pounds of nitrogen or maybe less. So this was very surprising because what is going on here? This is sandy soil. We don't see response curves like this. Um, and the other problem is without a true zero, we don't really know the full water quality effect. Without, did it really drop off on this side of the curve? If what is it a real drop off or is everything still actually relatively flat? And that's going to drive this water quality aspect, right? So these sort of gains of 40 pounds for an extra 15 bushels isn't necessarily super fantastic for water quality, but we can at least identify that there wasn't a benefit beyond it. Now, this site was kind of strange. So this is why like the other aspect of these studies is to make sure you're collecting a lot of these sort of diagnostics along the way. So we would not typically recommend using a pre-plant nitrogen test on a sandy soil just because the idea of something being there early, if something's there early, doesn't mean it's going to be there late on a sandy soil, right? But what we found this really interesting result where we saw a relatively high ammonium concentration. So at the time of planting, there was 136 pounds of nitrogen in the soil. Okay, so maybe an anomaly, maybe not. And even at the side dress time, we had 84 pounds of nitrogen in the soil profile. That's just in the upper foot. So there's a lot of nitrogen in the soil for whatever reason. Not quite clear why that was, but that definitely explains why the site wasn't very responsive. So collecting these sort of like extra pieces of information are really valuable. So for these non-responsive sites are super valuable, and you can really kind of assess like what's the true value that we got for each of these nitrogen rates. Now that's sort of like when you look at those non-responsives, though, I could say, do we could make the decision to say it's non-responsive and walk away. We explored a little bit, like, well, maybe a little bit of nitrogen was fine. Um, but that's why on that one, we got to check out what's going on. Is that typical with all that high ammonium in the soil at the time of planting, or is that just a 1 year anomaly? Okay. So that farmer, we definitely want to do another trial. Maybe not with the molasses, but we're going to work, but definitely more N rate trials to see if that was an anomaly year or not. All right, so what about the sort of responsive? This is on a sandy loam, right? So sandy, but obviously more not quite as sandy. Previous crop was snap bean. Um, first year of no-till. Now this site and when we varied the nitrogen rates, uh, the rate started with 100, meaning that there was 100 pounds applied at different parts of the season. 20 pounds in the starter, and then 80 pounds was sprinkled in through the fertigation. Um, the uh, sorry, the this would again we're side dressing with UAN at V3, so an in season, but just with the one timing. But so this is also a system where there's nitrogen going out at the edges. It's being doled out over the season. We're going to vary that rate at side dress. So we're looking at the efficiency of that side dress application. Okay. Um, with aerial, I love these aerial photos. You can definitely pick up the zeros. But are we picking up, what else are we picking up here? Not a lot. We can basically pick out the lows, and that's about it. All right, so sort of responsive. Okay, so we're gonna jump right into regression. An R squared of 0.27. Okay, all right. 27. The nitrogen rate basically accounted for 27% of the variation in yield, so a little bit better. This is one where the agronomic N rate was kind of outside of our N rates used, but because it's still relatively flat, and here we're using a 0.1 ratio, it pulls it all the way back to 188. Uh, then we look at each of these individual things, and we're seeing like really, we're getting the biggest bang for the buck, basically right up front, and then we definitely are losing return on investment. Here's the problem, though, right? With any of these things, the farmer didn't go broke by over applying nitrogen, right? They still, made money. Um, uh, so there's sort of this sort of, disconnect where we just aren't maximizing profitability, but we haven't, but even like we talk about these nitrogen applications, nitrogen is still, I mean, even though it's more expensive, it's still relatively cheap, right? I mean, even the idea of like, well, yields ticked up a hair. Well, they just made $40 less an acre, right? Is that going to make or break anyone? I don't know, but I mean, it has obviously tremendous impact on water quality, but it does demonstrate really kind of the sticky problem here, right? Especially with these flat response curves. Um, in any case, so when we look at these higher price ratios, pushes the pushes the EONR down. So it was 188 before when it was a little more favorable, but really right now in more sort of modern economic times, here we're really kind of maximizing the benefit with only 150 pounds of nitrogen. But what's interesting, we start to apply those sort of price ratios, it really didn't change where the optimum N rate was basically per N rate. It was just an overall reduction in the amount of money made. So what's the lesson here? It's like that price ratio influences the regression. It helps you move down, but it doesn't really change your ANOVA, right? So that's why we like to have these response curves. Hopefully they're more responsive and that generally we learn a little bit more. But here's the case of where even with 156 pounds, right? Or let's say they put out 40, 50, that's only 40 to 50, let's say 56 pounds at side dress. So they're getting in this system, they're getting a lot of value of that other 100 pounds, right? That 20 at starter and that 80 at doled out through fertigation. So they could really know that they're getting a lot of efficiency out of that, so they can cut back maybe on what they might need at side dress. And then you still need a rate that's going to be kind of in line with maybe some of the, with the 200 bushel yield. So your total rate's still 150, but because they're doling it out, you don't have to necessarily load it up as much early. So interesting results there. You can, again, we're only varying a certain rate, so we can't test the other things, but here clearly that extra 100 pounds was efficiently used. Uh, I'll also mention here there was an interesting also side study within this one where they put out it was a the plant this is all following uh this was planted green into a rye cover crop. Um, and then they also had one strip. They didn't vary the rate here. They just did one strip where they terminated the cover crop before planting. And interestingly, no yield effect. So in on these sandier soils, there was no difference in yield between planting green or terminating the cover crop early, which is kind of interesting. Because usually we see that big effect. We'll see that effect, kind of maybe we might see some yield declines on some loamier soils, but on the sandy ones and irrigated, maybe didn't not as big of an issue. Um, this is also this is just other nitrate data just to say that there was a good chunk of nitrogen. There's still 127 pounds of nitrogen at the time of planting, so that could also explain maybe a little bit of the lack of responsiveness. But once we got in season, there really wasn't much nitrogen in the soil profile at the time of nitrogen fertilizer application. All right, and the last case one is the responsive site. All right, so a loamy sand, so going back to a sandier soil. Previous crop was snapping. This also had a rye oat mix that winter killed. Here we also are starting with 100 pounds of nitrogen, where we have 30 pounds through the starter, a little more in the starter compared to the previous study. 70 pounds doled out through fertigation at V8, V12, and R1. And this is a side dress application at 32%. So here's another case where, well, we can pick up a little bit more here. We can pick up the zeros, and you can kind of pick up maybe that second lowest nitrogen rate, and then we'll kind of see where everything else, so greenness is tells you a little bit, but doesn't tell you the whole story. So this site was more responsive. There are the sites that have this like more sharp curve to them, generally nice curve, really good data, really high R squared. But now we got another problem though, is that we've got an AONR of 291 pounds of nitrogen and an economic N rate of 258. And that's with a price ratio of 0.1. This is the case of like again, and even we look at these sort of net returns from site to site, it was still up at this higher N rate produced the greatest return. Looking even at a more even at an advantageous one because the curve is a responsive curve, this is often what we'll see, that these price ratios don't really move the economic optimum rate that much. Here we go, right? So we go from 258, and now we go to we get more expensive nitrogen, only dropped it by 8 pounds. Okay. So what's going on here? Should the farmer put out 250 pounds of nitrogen? Well, unclear, right? So some of the problem is I don't love the efficiency, right? With 250 pounds of nitrogen to get 200 bushels, that is relatively low efficiency. That would put us in the low efficiency range um, in our sort of statewide benchmarks, right? So it'd be in the bottom quarter percent, the bottom 25% of efficiencies. For 200 pounds of nitrogen, or for 250 pounds of nitrogen, we need more yield in term to improve the efficiency. Otherwise, that's a fair amount of nitrogen loss. Another way to look at it is it would require 150 pounds in season at side dress that increase yield by only 60 bushels, right? That's even lower. So the efficiency of that 150 pounds, right? It'd be like this side dress rate, putting out 150. Uh, we're not getting a lot. We're not getting as much. We're not getting the return that we'd like to see. That's going to demonstrate that it was well utilized. Again, sticky problem. It's profitable, but it's having a disproportionate impact on leaching the groundwater. So what's the issue here? We varied the rates, right? We varied the rates at side dress. We can identify how much nitrogen was needed at side dress, but for this farmer, I would question what's going on with the rest of their nitrogen applications, right? Are they needed? If we didn't fertigate at all, would we get the same response curve? Right? So we've got an extra 100 pounds going out at other parts. In this site, maybe that other 100 pounds isn't being used that efficiently, and that's what we'd want to test. right? With those response curves for that second farmer, it looked like it was being fairly utilized, and then they know they could cut back. Here they got to apply, 150 at side dress, but maybe they're not getting the efficiency they were thinking with the 100 pounds. Because otherwise, at the end of the day, they got 250 pounds of nitrogen, but only getting 200 bushels. All right, so the takeaway is yes, these full nitrogen rate studies reveal a lot to the farmer. What the optimum nitrogen rate was, what their yield at their optimum nitrogen was, and their yield with no nitrogen or low nitrogen, right? Which also dictates the shape of the curve. Is this a field or a year where it wasn't responsive or highly responsive? And that's going to tell you where you're getting the bang for the buck. If your rates are higher, you want to see that sharp response curves. That means that the nitrogen is being utilized by the plant. If it's a relatively flat response curve, you're not utilizing as much nitrogen with each incremental gain. You also need to collect additional measurements to tell the story. You got to have soil samples. You got to have management history, especially when it comes to a lot of our other sites where it's like, what is going on here? Oh, it was alfalfa 2 years prior. Okay. That probably contributed some nitrogen. Oh, actually, they did have some solid manure application in the spring, right? All those other end inputs. Maybe thinking about the nitrate from the irrigation water on sandy soils like Guolong talked about. And then each nitrogen rate study reveals something for the farmer, right? The need for the need for lower nitrogen rates, right? In some cases, we could say maybe the need for higher nitrogen rates. The high use efficiency of the fertigation, the low efficiency of the fertigation, right? Every study was different, needs to be evaluated separately, and the things will be revealed, right? And that leads then to other decisions of what else need to be, what other experiments need to be tried, or what other trial and error type things need to be looked at for each farmer. So as we build this out, I think we have these studies, and then the next step is an integrate challenge for our ag water team here, right? And I'm looking at you, Izzy, right? Help create, we got to create these water assessment, the water quality assessments or the risk associated with the nitrogen rates used in this study, right? So to come up with that other curve where it's like, okay, it would really help like for the farmer that's applying 250 pounds. I don't think that they're going out and trying to seek to apply 250 pounds, right, to get 200 bushel. But it'd be also what's the story for that the farmer could also visualize like, well, what is the risk of water quality here? Oh, is that a lot more than I was expecting? Is that a lot more than my other fields? Is that a lot more than other fields and other farmers in the area, right? So which does clearly demonstrate there's some also advantage to mixing some stuff up. There's some efficiencies to be gained um, to and ways other to potentially cut back on your nitrogen and remain profitable. So with that, that's kind of the story. But and then as we kind of go through these, hopefully we're going to tell a lot of stories about this, and hopefully a lot of you are involved with maybe some projects like this or want to set up projects like this. And there's all these great stories and things to be learned um, as we move forward. Happy
Thanks so
to
much, Matt.
questions. Yeah.
Yeah. If you want to contact Matt or Guolong, their contact information is in the chat. But let's move on to answering some questions. Please, yeah, go ahead and put some in the Q&A box. Vote for the ones that you like. We will try to get to all of them. So, question from John. In general, is applying late N, such as V10 and on, with Y drops give enough bushels return to warrant the investment long term in combination with row and side dress application? So, detailed question. Any answers?
You know, I don't know, I guess is the answer, right? And these are one of these things that like if you have the opportunity to test that out, we're gonna start some work, with the Y drops in relative comparison to other things. But a lot of this is, what's the expectations here, right? It's gonna be a probability game, right? So like sitting around and waiting for us to collect, hopefully like, a dozen site years of data to tell you what. No, a third of the time it was more profitable to do that. It might be worth, trying to do some strip trials. You don't have to do full N rate trials necessarily either, right? If there's ways to kind of test it out, and that's going to always be a limitation of all of these little tweaks to the system, right? Split applying, certainly generally, well, I would the sandier the soil, generally the greater benefit. But unfortunately, we don't have a database, we don't have a tool that tells you X% of the time you're going to get a benefit by split applying with Y dropping late. So I think that's a tremendous area that we need to get more on-farm trials at to get at that sense of value. So, but unfortunately, we don't have the data sets, or we don't have those comparisons to really help provide you with that info.
Thanks, Matt. And there was a comment too, right after Guolong's presentation, that it would have been interesting to see the amount of nitrate leaching depending on different soil types. And hopefully you all saw that in the chat. Guolong brought forward a study. If you're into reading papers and studies, you can look into that. But Guolong, do you also want to address that comment now?
For sure. Yeah. So I briefly mentioned different ways to measure or indirectly estimate nitrogen leaching. The papers I tried to send through, which I think some people didn't see it through, so it's Zoom PDF messiness, um, is through these equilibrium tension estimators that are kind of the Cadillacs of measuring nitrate leaching. We have multiple setups of these measurement devices in different soil types. I think there's a set in Arlington um, that collected data through that for the corn example I used. There's a paper that's just been submitted to talk about nitrate leaching on sandier soils that Kevin Masaryk and his team worked on in the late 2010s. Um, so those two, I would say, are the most representative data sets. And then Matt's group presented a data set also on, I think that's early 2000, right, Matt? The lysimer data that you presented on,
Hmm.
that you published on. So I think the long story short, we do need more of these direct nitrate leaching measurements under different soil types, cropping systems and practices. And the practices are a lot harder to manage because running a nitrogen response trial on a farm is one thing. Putting these equipments on each of these under each of these treatments, it's another thing.
Great. Thanks, Guolong. Speaking of practices, we did get a question come in relating to the use of cover crops. So Eric wants to know, is there much N in that rye cover crop? And do we know if it's released in time for the crop to use? Either one of you.
All right, so this relates, if we're talking about sorry, was this a rye cover crop that we're talking about?
Yes, rye cover crop.
So this is the bad news, and I have to be the bearer of bad news. Rye takes up nitrogen, but it doesn't give it back that growing season. So when we look at all of these response trials we do, there's always the risk of needing more nitrogen. And then generally that risk increases the more nitrogen associated with is the bigger cover crop you grow. So cover crop, which tremendous benefits for water quality, right? Because the cover crop's taking up a lot of nitrogen, but you're planting into soil that has less nitrogen to start. Generally speaking, it's maybe on the range of, let's say, 40 pounds of nitrogen if you get about 2,000 pounds of biomass. So that's different than the legumes which supply. So the way that cover crops break down and decompose, they don't release it back. They don't release it back in time for the corn to use it. Now, so again, it's a good thing because then that nitrogen is most likely going to stay in the system, and they're going to, so with continued cover crop use over time, we can potentially be building the organic matter pools. Maybe we're increasing the amount of nitrogen supply for the soil. There's been some indication. We don't have a lot of long-term studies with cover crops, but there's some indication long-term use then leads to greater soil nitrogen supply, and maybe you get it back over time, right? So if you're growing a cover crop, a rye cover crop, I would say you can't expect it to, you don't expect that nitrogen to come back, and you're doing it for the long term. If you want
Yeah.
nitrogen to come back, the nitrogen to come back quickly, it's got to be a legume cover crop.
Thanks, Matt. Guolong, do you want to add anything to that?
And I just want to stress like the importance of finding these answers out on your individual farms, right? Because I think um like the one trial that Matt presented on, the cover crops did contain a decent amount of nitrogen within that site year, but it didn't affect yield as much as we expected. So I think it can really depends on where you are and what soil types you have and you know the year response in general.
Absolutely. All right. I'm going to try to sneak in one more question here, and then we will bring that CCA code up and you all can go on to your lunches. For the next step in water quality risk assessment communication, would excess nitrogen based on the end budget analysis be sufficient for a site like the responsive loam, sand loam example? And Brian also wanted to know who Izzy is. Izzy is on the call. Izzy is the ag water quality specialist for Southern Wisconsin, Izzy McNamee. So you can find her email if you're interested in this kind of thing and you're in Southern Wisconsin. She's your contact.
Everyone
But
should be
yeah,
peppering Izzy with questions.
there
Okay. So what was it? Was there a question? Sorry, I didn't catch what the question.
was a question. Okay, sorry.
I mean, if we're
For
going to use
the
it, so like using a nitrogen balance model on a loam, right?
yes,
Versus a sand where we know most of the direction is going to be towards leaching, right? It's not going to be as highly predictive. So usually what we talk about, and Guolong, I'm stepping on your toes probably, but the idea of potentially leachable, right? And I think this is going to come with like we have to figure out a way to deploy more to increase our ability to actually get direct measures of nitrate leaching. And I think there's a lot of interesting things that are going on, like with some sensors. We've got some sensors that are being developed. That's probably the frontier for a lot of our work here to see how well that actually connects. What's the actual risk? How much nitrate are we actually leaching? We don't have as much data on loamy soils as we think we do.
hmm And I would like to add, like, if you want to measure nitrate leaching, right, you can either use nitrogen budget model, which use your nitrogen input and output to estimate, right? If you don't want to measure, then a lot of the times you need to bury stuff. You need to bury either resin accumulators that Dr. Stephen Hall has been using a lot, or you can do suction cup samplers to take the dab at the soil water nitrate concentration as a proxy. Um, but I think a lot of the times when it comes to balancing the agronomic and the water quality is like how do we collect that extra layer of information? Um, and for soil types, it's with heavier soils, we might have higher mineralization fluctuations. So those are the things to consider when we are building these nitrogen balances.
yeah. Well, thanks so much for answering questions.